Okay, so today we're going to talk about optimization with geometry and modeling. Okay, so optimization problems, we have been doing, that's basically finding local extrema and global extrema. So today we're going to combine finding local and global extrema with mathematical modeling. So that's where, I'm going to give you a real world situation, and we have to somehow fit a formula to create a model of that situation. And then we will find extrema of that model to help answer the questions. So the key is to understand the function being optimized by looking at the situation in the problem and eliminating all but one variable. Then find critical points and endpoints. So basic strategy for solving an optimization problem is to first draw a diagram. Then find a formula for the quantity that's trying to be maximized or minimized. If you want to maximize volume, find a formula for volume. Then use all the given information to write that formula that you found in part B as a function of just one variable, right? Like volume would be length times width times height, but that's 3 variables. You can only have 1 variable. Find the real life domain of the formula. So if we were talking volume, length, width, and height, we would the real life domain would all be positive numbers because you can't have negative lengths, right? And then we use the techniques from the previous sections to find the extrema of the function that we develop. So here's our first example. We have a math book. It's to contain 36 square inches of printed matter on each page. And margins are supposed to be 1 inch along the sides, 1.5 inches along the top and the bottom. We want to find the dimensions of the page that will require the minimum amount of paper so that we can still get 36 square inches of text on a page and have the appropriate margins. So we're going to let L and W be the length and width of the part of the page that is printed on. So we should start by drawing a picture. So here's my page of a math book. So it's going to have a margin, 1.5 inches on the top and 1 inch along the sides. And then they said, let L and W be the length and width of the part that's printed on, which is like the inner rectangle. So we'll have this be length and width. All right, and we are supposed to find the dimensions of the page. So that would be this length and this length, okay, dimensions of the page. That will minimize the amount of paper. How do you measure the amount of paper that you're using? Area, yeah. Okay, so I want to minimize the area of the whole page. So if area of the whole page is what I'm trying to minimize, I have to come up with a formula for area. Okay. So without trying to eliminate variables yet, what is this, the height of the page here? W plus 3 or 3 plus W, yeah. Because this is W, right? It doesn't really matter. I suppose, yeah. We can call it L. We'll switch them. That feels more familiar. L and W. Okay, so this length here is now L plus 1.5 plus 1.5, which is L plus 3. And what is the width of the whole page, not just the printed part, but the whole page? W plus 2. Okay, so I now have a formula for area, but the problem is that it has two variables in it, a width and a length. Is there any more given information that I could use in order to substitute in for one of my variables? Yeah, the inner part, the printed part, is 36 square inches. So if I use that other info, other given info is that length times width has to be 36, because L and W are representing the length and width of the printed part. So that has to be 36. So I could solve for one of these variables. Let's say, I don't know, length. That would be 36 divided by W. And then I could make a substitution in my formula for area. So I now have area is, instead of L plus 3, it'll be 36 over W plus 3 times W plus 2. So now I have a formula for area, and I need to minimize it. I have to find out what value of W will make the area of the page smallest. And then once I have that, I can figure out what L is, because L is 36 over W. All right, so take a few minutes and minimize this. Interrupt you for 1 second. So we're trying to minimize this on what interval? What interval of W makes sense for this problem? What's the smallest W could be? 0, but not 0, because if we made W 0, there would be no page, right? So, but we could make it really, really small, right? So we'll put 0, but not including 0. And then what about the biggest W could be? Infinity, yeah, because we can make W as big as we want. It just would make L really, really tiny. So our interval that we're looking on is 0 to infinity to minimize this guy. So it might happen at near an end point, your minimum, or it might happen at a critical value. All right, let's go through it together. If we're looking for a global minimum, right, the lowest point in the domain, because I really want to have the lowest possible area, then I need to find critical values and then also check the endpoints. This is an open interval, so I have to see what happens near the edges, because you can't actually get to 0 or infinity. So things I need to check are critical values. I need to find the critical values and find the value of the function at each of them. And then also I need to know the limit as x approaches infinity of the area function, and the limit as x approaches 0 of the area function. And really, I only need to approach 0 from the right, because that's the domain. The left of 0 isn't in the domain. All right, so let's do these two limits first. The limit as x approaches infinity of area, which is 36 over W plus 3 times W plus 2. All right, what happens to 36 over W? Oops, I should have used a W. What happens to 36 over W as W gets really, really big? It gets closer to 0. So we have something that's approaching 0 plus 3 means that this whole thing is going to go to 3. And W plus 2, what happens to that as W gets really, really big? Approaches infinity. So I have a product of 3 times infinity. What's that going to go to? Infinity. So as I make my width smaller, the size of my page just has to get bigger and bigger and bigger to accommodate having that small width. And then let's see what happens as I make my width smaller. The limit as W goes to 0. Okay, 36 over W. As W goes to infinity, as W goes to 0, what happens to 36 over W? Goes to infinity, and it's going to be positive because I'm approaching 0 from the right. So this is infinity plus 3, so this whole thing is going to go to infinity. What's going to happen to W plus 2 as W goes to 0? It's going to go to 2. So I have infinity times 2, which is infinity. All right, so at the edges, when the width is really big or the width is really small, we are getting really, really large areas. Okay. So it seems like the minimum is going to be not near the endpoints. Near the edges of the domain, the area function just gets huge. And we want to find the minimum. So it's probably going to be found at a critical value. So let's find critical values. (36 over W plus 3 times W plus 2. All right, where do critical values happen? When the derivative is 0 or undefined. So I need to take the derivative. I could take the derivative just like that. I could use the product rule. Or you could FOIL it out and then take the derivative of each term separately. Doesn't matter. I don't think one is any easier than the other. So maybe I'll just use the product rule. Okay, so A prime is going to be first, 36 over W plus 3, times the derivative of the second, which is 1, plus the second, times the derivative of the first, negative 36 over W squared. Yeah, so you would rewrite 36 over W. You could think of that as 36W to the negative 1, and then you can apply the power rule. So you'd get negative 36W to the negative 2. And that ends up being negative 36 over W squared. All right, so is this ever undefined? Are there any values of W that you can't plug into that function? 0. Okay. So A prime is undefined at W equals 0. Not a super important value because 0 is not part of our domain anyway. So we would never choose a W of 0. So now what I need to know is where is A prime equal to 0? All right, ideas? How are we going to solve this? Simplify the left side a little bit. Sure, what do you want to do? Okay. In the first term, I can get rid of the 1. I don't need those parentheses. And then in the second term, I can just multiply these two. I'm going to distribute the negative 36 over w squared. So w times negative 36 over w squared is going to be negative 36 over w. And then negative 36 over w squared times 2 is negative 72 over w squared. All right, what do you see? A 36 over w and a negative 36 over w. Those terms cancel. So I now have 3. I'll move that to the other side, equals 72 over w squared. Multiply both sides by w squared, so I have 3w squared equals 72. 72 divided by 3. That seems big. It could be 24. Okay. So that means that w, technically it would be plus or minus radical 24, but we're not considering negative values for w, so I'm just going to write the square root of 24. There's my critical value. Am I sure that it's a minimum? The end behavior goes towards infinity, right? And we have a critical value, which means we have a horizontal tangent line. So it's got to be, if you have a horizontal tangent line, it's either a min, a max, or one of those flattens out and keeps going up kind of places. But let's see if it's possible to draw it without it being a minimum. So here's radical 24. I know that at the endpoints of my interval, my graph goes up, right? And so if it was one of those places where it flattens out, but doesn't turn around, I couldn't have this end behavior. And if it was a maximum, I would have to have 2 other critical values to create that end behavior. So I know it has to be a minimum. What if I wasn't sure, though? What if reasoning that out was more difficult for some reason? What could I do? I could make a sign chart to show that it's a local min. Yep. And then I would say the endpoints go to infinity. This is a local minimum. It has to be a global minimum because there are no other critical values. All right, so I have the width. I was supposed to find the full dimensions, right? And I'm supposed to find the full dimensions of the outer page. So I just solved for W, which is the width of the printed part. So the outer part would be W plus 2. And I need L, which is 36 over W, and the outer L, which is that plus 3. All right, so W is radical 24. L is going to be 36 over radical 24, 36 over W. And then the outer dimensions are going to be W plus 2 and L plus 3. Or radical 24 plus 2 by 36 over radical 24 plus 3. And if someone who owns a publishing company came to you as a professional mathematician and asked you, how am I going to minimize the area of this page and still have 36 square inches of text, and you told them this, they might be kind of annoyed at you, right? Like, could you just tell me a real number? Well, these are real numbers, right? No. We'll give them a decimal approximation. So radical 24 plus 2 is 6.9. And then I need 36 over radical 24 plus 3, 10.3. All right, how can we check that that answer is correct? Okay, we'll just graph the function. So it was 36 over W plus 3 times W plus 2. And our domain is 0 to infinity. So I'll start at 0 and go, let's see, we found the minimum at 6.9. So I'm going to use this to help me set my window. Maybe I'll go to like 20 inches for W. And then for Y, this is the area. What's 6.9 times 10.3 like approximately? 70 something, yeah. So that's the minimum area, we think, right? So we're double checking, but we think that's the minimum area. So I'm going to go 0 to 200 square inches. And it does appear that there's a minimum here. And we were right about the end behavior. It goes to infinity near 0, and that looks like it's going to be heading up towards infinity. So I do second calculate, minimum, give a left bound and a right bound and a guess. Oh, whoops. And I got 4.9. Because of the what? Oh, yeah. Right, because that's the W. That's not, doesn't have the plus 2 on it. Whew. So that doesn't have the plus 2 on it. Good. So that confirms. That is radical 24. Yeah. Good. All right, one more that we'll do together, and then I'm going to have you work on dogs do calculus. Okay, the Postal Service specifies that boxes sent through the mail have to have a length plus girth, and girth is the perimeter of a cross section of no more than 108 inches. So we want to find the dimensions of a box that has maximum volume that can be sent through the mail. Assuming width and height, that is the cross sections of a long box, have equal or squares. So if I draw a picture of it, which I'm terrible at, let's see. So we've got like a square base, and then we've got another square base for the top, and then get the idea? I'm so bad at this. I want some dashed lines here. Okay, so there's a box that we're sending through the mail. Long box. We're assuming that the base is a square that has equal length and height, so we're going to call these guys, we'll call them x. Right? And then we will call the length of the box L. All right, so the Postal Service says that the length plus the girth around can't be more than 108 inches. And we're trying to maximize the volume of the box. So we start by saying what we're trying to do, maximize volume, right? What is the volume of this box? X squared times L. But it's got two variables. I need to use some more of my given information to try to eliminate one of the variables. And that is the restriction that the Postal Service has, that the perimeter around the box plus the length of the box has to be no more than 108. So we're going to make it 108 because we're trying to maximize volume. So take all the space that they'll give us here. So what is the perimeter around a cross section of a box? 4x, yep. So 4x plus the length is 108. That's the Postal Service restriction. So you can solve for one of these variables. L would be easy to solve for. And then I can plug it back in my other volume equation. So volume is x squared times 108 minus 4x. And I want to maximize volume now. I want to find what x should I choose, what x and L, to make maximum volume. Okay, what's the smallest I would want to make L, or that I could make L? Approaching 0. Same for x, right? So something teeny tiny, but not 0, because then the box won't exist and we'll have no volume, right? And then the biggest I could make x. (108) divided by 4, and then my length would be 0, and there'd be no box. But so I'll make it a round bracket and say you can approach that, but you can't actually make it that. So what's 108 divided by 4? 27. So 0 to 27, open brackets, because if you choose either of these endpoints, your volume will be 0, which doesn't make any sense because we want to maximize volume. Okay, so I want you to take a few minutes, maximize this function on the interval from 0 to 27. Okay, so let's look at maximizing this thing on the interval from 0 to 27. We need to check near the ends of the interval and critical values. So we already discussed, actually, we didn't use limit notation, but we already said near the ends of this interval, the volume is getting closer to 0. Right, so I could say the limit as x approaches 0 of this volume function. Okay, if x gets close to 0, this x squared term gets close to 0, and the whole function gets close to 0. And then the limit as x approaches 27 of the volume function. 4 times 27 is 108. So as this x gets close to 27, this term, this factor in parentheses gets close to 0, and the whole thing gets close to 0. So I'm pretty sure that I'm not approaching large values, that I'm going to have a maximum somewhere in between. So check critical values. So volume, I'm going to distribute that x squared. I think it'll make taking the derivative easier. 108x squared minus 4x cubed. And then I take v prime, because critical values happen when v prime equals 0 or v prime is undefined. So v prime is going to be 216x minus 12x squared. Is that ever undefined? Nope. So I just got to set it equal to 0 and solve it. What do I do? Factor out an x. And a 12, okay. What's 216 divided by 12? 18. Minus x. Did I do that right? Yeah. Okay. So either x equals 0 or x equals 18. So that critical value is a potential max or min. Which one do you think it is? It's got to be a max. If the ends of the interval go to 0, and we have this 18 as a maximum, I don't think there's any way that it could be a minimum or a like flattening out and continuing kind of thing. But just to verify that this thing is a max, we've done sign charts a lot. Let's use the second derivative test to verify that this is a max. I don't think we've done it together in class since the day I presented it, so just as a way to remember. Okay. So the second derivative test says that if you have a place where you have a horizontal tangent line, you can tell if it's a local max or local min by looking at the concavity at that point. Right? If you have a horizontal tangent line and the graph is concave down, it has to be a max. And if you have a horizontal tangent line and the graph is concave up, it would have to be a min. So we're going to look at the concavity at x equals 18, and the concavity comes from the second derivative. V double prime would be 216 minus 24x. And this problem is a good candidate for the second derivative test because it's not hard to take the second derivative. All right, and then we're going to plug in the point of interest, 18, and (216) minus 24 times 18 is negative 216, which is less than 0. It's a negative, which means the graph is concave down there, which means that this x equals 18 has to be a local max. So V is concave down at x equals 18. So we have a local max. All right, have we fully answered the question? What did they ask us to do? What dimensions? Find the dimensions of the box with maximum volume. Okay, so we found the x value. We just need the L value for the length of the box. So we know that 4x plus L is 108. So we could solve for L by putting in 18 for x. Nope, not 72. What's 4 times 18? Yeah, 72. So L is 36. So the dimensions of the box would be 18 by 18 by 36. And then the volume of this box I would get by multiplying those together. 11,664 square inches. Yes. Cubic inches. So I was just thinking about it while you were working. It seemed like an arbitrary restriction for the post office to put, like, that the perimeter around plus the length equals 108. What do you think? Is it arbitrary, or do you think there's a good reason for it? Yeah, it does stop you from having a really long box. So the longest it could possibly be is 108 inches, you know, if your perimeter around was like teeny, teeny, tiny. So that is like, maybe that has to do with the length of their truck, right? And then if the length were really, really teeny and it was just a square that was really, really thin, the dimensions of that square, the biggest it could be is 27 by 27, which is like manageable carrying size, like less than 3 feet. I don't know, just a guess. Okay, so I'm gonna have you work on this group activity. We're not gonna leave 10 minutes for anything at the end of class. So this problem is based on a paper called Do Dogs Do Calculus, published in 2003. So this is a real experiment done by a mathematician, and he found that the paths that his dog Elvis took to the ball were remarkably close to the optimal paths found by calculus. If you treat this like an optimization problem. The paper you can find online if you're interested in reading it. So a math professor is walking his dog Elvis along the shore of Lake Michigan, and Elvis likes to chase tennis balls, which the professor tosses into the water some distance ahead of him. So he throws it ahead, not just directly out into the water. So Elvis could swim directly to the ball. He could just go straight into the water and do a straight line from him to the ball. But he can run much faster than he can swim. So it's more efficient for him to run along the beach for some distance and then swim out to the ball's location. Okay. So the situation is summarized by this diagram. Point E represents Elvis. Point B represents the ball. So the shortest distance would be for him to swim directly to the ball, because this is the shoreline right here. And then line EC runs along the beach. And Elvis is going to run from point E to point D and then swim from D to B. Okay, so we want to know how far should he run, right? How far should D be from E to make the time it takes for him to get to the ball the fastest, shortest amount of time. So we're assuming that CE is 20 meters and BC is 5 meters. And X is the distance between points D and C. All right, so I'm going to have you work through it in your groups.